we defined the surprise of a random outcome x to be the log of 1 over the probability of that outcome. Now, just as a tidbit, it is pretty customary to use log base b, where the base b is the number of possible outcomes of the random variable x. In our case, when we were looking at red balls and green balls, there are 2 outcomes, and so what we're looking at up here is the log base 2 of the probability of x. Sorry, 1 over the probability of x. Now, in order to utilize the idea of surprise, let's recall that given a series of independent events, we'll just label them event 1 all the way up through event n, the probability of them all occurring is the product of their individual probabilities, provided that they are, again, independent, meaning the probability of a subsequent event is not changed or affected by the likelihood of a previous event, or the occurrence of a previous event, rather. And so the probability of E1 and E2 and all the way up to event n is, in that case, the probability of E1 times the probability of E2 times ... times the probability of E sub n. That's going to come in handy because it turns out that the surprise associated with independent joint events is the sum of the individual event surprises. For example, let's take a look at scenario 1. We already observed that there is a 40% chance of drawing a green ball, and a 60% chance of drawing a red ball. These were the 2 possible outcomes. We draw a red or we draw a green. Now, what would be the surprise of drawing a red ball followed by another red ball? Well, according to our definition, the event x is this outcome right here. It's the probability of drawing 2 reds. So using our concept of how we define surprise to be inversely related to the probability of the event, we would have 1 over the probability of that outcome, of getting 2 reds. And the probability of getting 2 reds, because we are, if we assume that we replace the balls back into the pool, then the likelihood doesn't change, and so we would expect to have a 60% chance of drawing the first red, followed by a 60% chance of drawing the second red. Now here's where it comes in handy to recall a couple of properties of logs that will help us support the notion of this theorem. We won't need all of these right now, but I'll just go ahead and list them out. The log of a product of 2 quantities is the sum of their individual logarithms. So log of a times b is the log of a plus the log of b. And property 2, the log of a divided by b is equal to the log of a minus the log of b. And even further, one more thing that's actually related to the first is the log of a to the power of b is equal to b times the log of a. So these will come in handy, but if nothing else, we get to review them here. And what we're going to do is we're actually going to write the expression here in parentheses as the log of 1 over 0.6 times 1 over 0.6, because that still is the same thing as 1 over 0.6 times 0.6. And by property number 1 here, the probability of a product is equal to the sum of their individual probabilities, of their individual surprises, like that. And we see that hey, this is just the log of 1 over the probability of red plus the log of 1 over the probability of red. And hopefully now you can see that it's exactly what we're stating in our theorem. The surprise associated with independent joint events is the sum of the individual surprises. Well, because this is the surprise associated with drawing a red, plus this other term is, again, the same thing, the surprise of drawing a red. Now, the same thing would hold if we wanted to draw 30 reds, right? It would be 30 times generate the same outcome. We could also have greens in there if we wanted to. That would not make a difference at all. Now, one question we may want to answer, and this will lead us up to the definition because we're here for entropy, but what does surprise have to do with entropy? Well, it turns out that entropy is the average surprise associated with your probability distribution. So we're gonna focus on drawing 100 balls, only because it's a nice round number. It's easy to divide and multiply by 100. And so what would we expect the outcomes to look like in those 100 drawings, assuming we're replacing balls back in the pool? Well, we could either draw reds or we could draw greens. There's a 60% chance of drawing a red, a 40% chance of drawing a green. Probability tells us the relative frequency of expectation for each of the outcomes. So of those 100 draws, we would expect roughly 60 of them to be red and roughly 40 of them to be green. Right? That's how we would expect. It's probably not going to come out exactly this way, but that's the expected average outcome. Okay, well, that means that I now need to know, well, what is the surprise associated with one red and with one green? Because if I draw 60 reds and then 40 greens, that's just going to be 60 times the surprise of a red plus 40 times the surprise of a green. So let's do this. We'll make a little table here. And we'll list out for red and green, we'll list out, well, what is the associated probability and what is the associated surprise? Well, the probability of a red, we already said, is 0.6, and the probability of green is 0.4. The surprise associated with a single red, okay, if we're going to stick with the concept of there are two outcomes, and therefore we would use a base of 2 to stick with what is customary. Now the surprise of a red would be the log base 2 of 1 over the probability of a red. And using the calculator, we can compute these, but for the green, this would be log base 2 of 1 over 0.4. We've already said that the surprise associated with well, actually, we haven't defined that yet, so let's calculate it. So the surprise of drawing a red ball is about 0.74, and the surprise associated with drawing a green ball is 1.32. So notice that indeed, events with higher likelihoods have lower surprises, and events with lower probabilities have a higher surprise. Okay, great. So now that we have that, if we want to compute the total or the average surprise, well, we're going to have 60 outcomes, which, recall, that's the way we got 60 was by taking 0.6 times 100. So this is simply 60, but I'm going to write 60 like this for now. Okay, that's my 60. And I'm multiplying that by the surprise associated with a red because, again, recall that what we just proved up here is that the surprise associated with independent joint events is the sum of the individual event surprises. So if you get 60 reds, then that's going to be 0.74 plus 0.74. Well, it's going to be 60 terms of 0.74, which is the same thing as just taking 60 times 0.74. The surprise associated with drawing our green balls, well, it's going to be 40% of the 100. That gave us our 40. And we're going to multiply that by the surprise of drawing a single green, which is 1.32. And now we are going to add these together, right? Because we've already said that the surprise associated with joint events is the sum of all of their surprises. We have 100 total surprises, 60 of them are 0.74s, 40 of them are 1.32s. We're adding them all together. And now we wanted the average, right? So this is the total. What we have here is the total. And we know that to compute an average, we have to divide by the number of things there are in that average. So let's divide this by 100. And immediately what I want you to see is that is really just an expected value. The fact that we're multiplying by 100 in each of these terms and dividing by 100 means we could factor out a 100 from the numerator and cancel that out with the 100 from the denominator. And so notice that the average surprise here is really just the probability of the outcome times its surprise of 0.74 plus the probability of the other outcome times its surprise, which is 1.32. So what we get when we calculate this is an average surprise of about 0.972. And this is our average surprise. So the 100 didn't really matter at all. It doesn't matter whether you draw 100 balls or 1,000 balls, your average surprise will be 0.972. After all, if we drew 200 balls, then we would just have 200 in the numerator in place of the 100s, and then a 200 in the denominator, and once again, the 200s would cancel out, and we'd get an average surprise of 0.972. So this is the average surprise per draw. Right? This takes into account the fact that sometimes you have a high surprise, sometimes you have a low surprise, and normally you're going to have something probably a little bit closer to 0.74, right? Because the 0.74 is going to occur more often than the 1.32. So 0.972 is a little closer to the 0.74 than it is to the 1.32. Now, let's do the same thing for scenario 2, and we would expect here our average surprise to be perhaps higher because, let's find out. We have red occurring 90% of the time, which we would expect 90 reds, and again, we would only expect 10% or 10 greens, and based on what we did here, all we really need is this table. Probabilities in this table, 0.9 and 0.1, and the associated individual surprises, which would be the log base 2 of 1 over 0.9. Log base 2 of 1 over 0.9 this one comes out to about 0.15. So you can see this one is significantly lower than all of the surprises because it's highly common. We wouldn't be surprised at all if we drew a red. But we would be surprised if we drew a green. And this one comes out to about 3.32. So you can see much, much higher than the other ones. But how does that affect the average surprise? Well, once again, the average surprise is simply going to be 0.9 times the associated surprise. Remember, just the expected surprise. It's an expected value. 0.15 plus 0.1 times 3.32. And this comes out to 0.9 times 0.15 plus 0.1 times 3.32. This one comes out to about 0.47. You're like, well, wait a minute. And I think I said this surprise would be higher, but my thinking was the surprise associated with the low likelihood outcome, that surprise is going to be quite high. But notice that the average surprise per draw is actually considerably lower, right? In this situation, we would be surprised a lot less often on average than we would over here. Now, the surprise associated with, say, drawing 2 greens in a row would be incredibly high. It would be 6.64. So what we're saying here is getting 10 greens and 90 reds is pretty much what we would expect. But let's say you did get 10 greens. Well, that would give you a total surprise of 33.2, which would be obviously a lot higher because you were getting 3.32 surprise per draw since you drew 10 greens in a row. But in this situation, we would expect very little surprise because we would expect to get reds almost all the time. And now finally, to our definition of entropy. Entropy is simply the average or expected surprise. Okay, so the entropy of a random variable x is, and I want to use this definition here. Notice that what we did is we took a probability of red times the surprise of red. And oh, by the way, the surprise of red, remember that that is the log of 1 over the probability of red. Plus we took the probability of green times the log of 1 over the probability of green. And that is our entropy. So we actually calculated the entropy to be 0.47 in scenario 2, and the entropy in scenario 1 was 0.972. And that's all entropy is. It's the average surprise per outcome, given our probability distribution. So this is the actual formula, and it looks crazy, but it emerges naturally through what we just developed. Now, if you're wondering how these two things are equal here, let me show you. We can use a property of logarithms. The property of logarithms where if we have a ratio is the log of the numerator minus the log of the denominator. If we took this guy here and we wrote it as the log of 1 minus the log of the denominator, which is p of x, well, the log of 1 is 0, and you get negative log of p of x. And so simply by taking that negative 1 and factoring it out front, like we have it here, this is just a negative 1 right there, then you could also write it as p of x times the log of p of x. Which one you use doesn't make a difference. They're exactly the same. This one kind of emerges a little bit more naturally, but they both produce the exact same measure. So to recap on all of this, entropy is a measurement of how surprised we should be on average by the outcomes of a random variable x. Higher entropies mean a greater surprise and smaller entropies mean a lesser surprise. More specifically, we are considering the entire probability distribution of x. Notice that just like an expected value, our probabilities that we use have to sum up to 1. We have to consider every outcome within that distribution. Therefore, the entropy tells us how surprised we will be given x's outcome probability.